Physics, law of conservation of energy with springs. So for this example, we have a block with a mass of 2 kilograms, and it is sliding on a horizontal frictionless surface with a velocity of 2.5 meters per second. The block strikes a spring with a spring constant of K equals 4 times 10 to the third newtons per meter. So assume the impact is elastic, which means that both kinetic energy and momentum are conserved. Alright, so for this, we need to find what is the initial kinetic energy of the system. Then B, what is the kinetic energy of the system when the spring is compressed to x equals 1 centimeter. So that means that when the spring is compressed basically 1 centimeter from where it is normally. And then C, how fast is the block moving at this point? So, as with all problems, the first thing we should do is find out what we know about this problem. So our knowns are, we know the mass of the block is 2 kilograms. We know the velocity, the initial velocity, is 2.5 meters per second. We know the spring constant for the spring is 4 times 10 to the third newtons per meter, and the displacement is 1 centimeter, which is also equal to 0.01 meters. So we are looking for the initial kinetic energy. We are looking for the kinetic energy of the system after there's a little bit of compression in the spring, and then we are looking at how fast the block is moving after the spring has been displaced that 1 centimeter. So, just to give you an idea, drew a picture here, and basically it's an attempt at a horizontal frictionless surface with a block sliding toward a spring. So for this we have the initial state, which is right before the block comes into contact with the spring. So right before it has the initial velocity of 2.5 meters per second, and the spring is uncompressed. So then next we have the state 2, where the block has basically displaced, or not displaced, it has compressed the spring just a little bit, just 1 centimeter. And now we're going to go ahead and see if we can't find out some of the information for this problem. So first off, we need to find the energy at these states. So we know kinetic energy. Well, actually, let's go ahead and do total energy. So the total energy at state 1, so we're just going to call that E sub 1, is equal to KE1 plus SE1. So KE1 is kinetic energy at state 1, and the spring energy at state 1. And then for the second system, energy at state 2 is equal to kinetic energy at state 2 plus spring energy at state 2. Alright. So with this, we can actually go ahead and start determining a few things. So for KE1, we know that there is no spring energy. And so we can just say KE1 is equal to 1/2 mass of the block times velocity, the initial velocity, squared. And when you solve this, E1 is equal to 1/2 times mass of the block, 2 kilograms, times velocity squared times 2.5 meters per second quantity squared. And your KE ends up equaling 6.25 joules. And this is actually our answer for KE1. Alright, so with this, we also know the spring energy at segment 2. So to find the total energy, basically we know that there's no energy lost in this system. So your energy at state 1 is equal to energy at state 2. So technically, because we canceled out the spring energy, KE1 is equal to KE2 plus spring energy at 2. And we can actually go ahead and solve for KE2. So we can say KE2 is equal to KE1 minus spring energy 2. And we can go ahead and plug in the some of the variables for that. So we know that KE1, we already solved for it from before, is the 6.25 joules. And then we know spring energy is going to be 1/2 kx squared. And we can go ahead and plug in and solve for that. So that's going to be 6.25 joules minus your 1/2 times your 4 times 10 to the 3rd newtons per meter times your 0.01 meters squared. And when you solve for this, you find that equals KE2, which is going to be 6.05 joules. And then we can go ahead and derive the value for V2, so the velocity at state 2, and we can do that by breaking down the KE2 into its components. So that's going to be 1/2 times mb times V2 squared. Solving for V2, V2 will be equal to KE2 times 2 divided by m sub b to the 1/2, which comes out as 2.46 meters per second is equal to V2. And so as you can see, there's not a giant change inside of the actual velocity. However, if there were to be more spring compression, because it's squared, the value would decrease significantly until, of course, it just rebounds. And that is all for law of conservation of energy with springs.